Okay, so we must understand how ParaView does its trick. It's all about a discussion about the visualization pipeline. And here, Ken again had published a nice article in 2013, which I took as an example. There's the concept of this visualization pipeline. What is a pipeline? Basically, a data flow. You read some data into a particular process. You do some filtering. So one example of a filter is an isosurface, right? A 3D representation of a scalar field at a fixed threshold. And then you make an image of it. So we have what we call the sources, the filters, and the sink. The sink is the producer of the image. The modules are functional units. They can have 0 or more input ports. So a reader does not has 0 ports, basically. Isosurface has 1 input port and 1 output port over here. And the render here, again, only has input ports. And then you can have multiple ports, and then you can have branches into this pipeline. I'm hoping you have seen that already in your visualization, in your pipeline browser on the ParaView graphical user interface, where it shows you the tree of filters. All right. The connections really show how data moves from one module to the next. Now, execution can be event-driven. For example, you click on a button, or you type a particular command, and then you trigger the execution of any module on the pipeline. Or it can also be domain-driven, in that most often it is the case, the renderer demands, the renderer asks for execution. So basically, there's a pipeline ready to execute, but which has not yet executed, and then it gets triggered. So there are basically 3 passes in the execution. One of them is where the sources, at the top of the pipeline, the sources advertise the content they can generate. So what are those informations? The number of time steps, the number of variables, the name of the variables, the size of the grid, the type of the grid, etc. All those things describe your data. It doesn't mean it reads it. It just says, this is what I have stored in my data file. So that description in the first pass goes down all the way to all the modules in the pipeline. There's no execution yet of reading the data. The second pass, the application decides which region the sink, over here at the bottom, should process. Now this seems redundant, maybe. If you have a single processor, well, of course, I'm going to read all the data. But you need to think in parallel. If you have multiple instantiations of this pipeline, then each sink should do a sub-volume of data. So this is where that decision takes place. The sinks decide which region they are capable of dealing with. So that information goes back up to the source. And then the third pass is the actual execution. Each source generates the data it needs to execute the pipeline. Let's think in parallel. In parallel, ParaView will take your pipeline and make as many copies of the pipeline as there are PV servers. So they will be identical. Perhaps there is some communication at an intermediate stage of the pipeline between filters. But basically, there will be a different piece of data for each parallel pipeline. And I need to be careful about saying pieces and not volumes. Because if you have, for example, a cloud of points, what does it mean? A subvolume? Well, yeah, you can take your cloud of points and separate it into different pieces again. So piece is the best word to use. If you have a structured grid, for example, the grid of before of size 2048 by 1024 by 1024, you can easily divide this grid into one piece, which is 1024 cube, and a second piece, which is 1024 cube. And then you can run on two processors, and then you would have two pipelines. Now the decision about splitting a volume, like I said, two pieces of 1024 cube or more pieces, that decision is left to the ParaView executable. So my pipeline again, I have source, filters, mappers, rendering, and this is an example of the pipeline browser here, where this is the source. The first filter that gets attached to it is a contour filter. From there, I can do an histogram. From there, I can do an extract edge, so I have a multiple output out of this filter. And then using the same source again, I have here, actually, yeah, this is just a second source here in my pipeline. So I can have multiple sources, each of them with a particular pipeline like this, which can branch out. And ParaView will manage in parallel to subdivide each data set into pieces of equivalent weight. So I'll try during the next couple of days to show you when this two-way execution is actually taking place, because most of the time it's so fast that you don't realize it. But I'm going to actually give you an example right away. Some filters will have to exchange information. So for example, the ghost cell generator. What are ghost cells? Can someone give me a definition of ghost cells? What are they?
It's a cell that stays at the boundary of the domain.
Okay, very good.
Contains information on the boundary of the other processor.
Yes, very good. Yes, I'll repeat the question. So ghost cells are, as you said very well, cells which are on one side of a processor boundary, and they contain information from the other processor next to that boundary. So they are useful, for example, in the computation of a gradient. If you have a volume of data split in two to compute your gradient, you still need one grid line on the other side of your boundary, on the other processor. So when are ghost cells necessary? The answer is not always. If you want to read your data and just make an image of it, the outside image, the outside surface like I've shown you before, I have to be careful here. without using normals. Normals are the vectors which point in the direction perpendicular to the surface. You can do it without ghost cells. So what would happen? Each pipeline would read one piece of data quickly and make an image, and then ParaView in parallel composites all the images of the independent renderer and make the final image that you see on your client side. Good, everything is good. Then I ask for an isocontour filter inside this distributed pipeline. What happens? I put here an isosurface. The isosurface, to be coherent, to be contiguous, to be clean, needs information from the other processor's boundary. It needs ghost cells. Well, wait a second. The first time I executed my pipeline, I did not create the ghost cells because I didn't need them. As soon as you put in an isosurface filter here, it will re-execute the full pipeline, asking the reader to generate its own piece of the data plus the ghost cells. Basically, you're doing twice the work, and it's costing exactly twice the time. So this is what I will teach you to avoid. If you know you need ghost cells, you need to do it in a different way. Another example, which is not parallel, but still, here. I read my data. Well, I have the reader source. Suppose, instead of the isosurface, I only want to take one slice through the middle of the volume and make a picture of it. The question is, should I need to read the full domain to do just one slice of it? It would be good to be able to avoid that. So I have exactly that demonstration ready for you. I will restart ParaView here and turn off the parallelism in it. Apply. Okay. Exit. I have prepared here a script, a Python script, which will read exactly one slice of my data. And you saw how fast it was? I hope you saw that. There's one slice of my data. And the absolute best of it is the memory usage. Remember that dataset was 8 gigabytes, the volume. I've read one slice of it, and I'm only consuming 400 megabytes of data. This demonstrates that I have not read the global volume. I've only read exactly the slice of data I wanted to make a picture of it. So all of this requires I'd like to say an intimate knowledge of the reader. So is my reader parallel aware? Is it capable of splitting the data? Yes. If so, in that case, I can ask my reader to read exactly the subdomain I want. So let me show you the script. And you'll see the there it is. This is the Python script. Image reader, that's the full name, float. This is the extent, 2048 by 1024 by 1024. But I have not read the data yet. I've only described the content of the data. Here's the slice, extract subset 0, 247, 512, 512, so it's exactly halfway through. Actually, yeah, in the y direction, the halfway point is 512. And I execute this, and I was able to extract only one. I was able to read and extract only the slice of data that I was interested in. How did this happen? This Python code here, you can read it sequentially, but it does not execute sequentially. There's a special keyword here, special command called reader, update pipeline information. This is exactly the first pass I have described in my slides here, the first pass of the execution. I advertise the data that is available. The reader object here says, I am capable of producing data as big as this, but I wait for you to tell me what you need. The extract slice says, this is what I need. I only need the 512 slice through the data, and I execute. So this is how you can prototype your big visualization on your laptop. In fact, that animation I showed you of this big volume, then I was entering the volume, I was navigating through the volume. I did all this with a slice of data. Just a slice through the middle volume, just to give me the point in space where to go, and I was done.
How would you do the diagonal cut if you tilt the angle?
Very good question. How would you do the diagonal? You could not. The answer is you can't. You pardon me?
In this animation.
No, what I showed you, it was something else. Let me read it again. There. It's me changing the orientation of the camera here.
Fire animation. That one.
Yeah, in the fire. That is the final production, so it uses the full resolution data. Okay? So here I'm only reading the slice through the volume. Now, oftentimes it's useful to show the bounding box of a volume, right? It shows the minimum and maximum XYZ space. Why am I not showing it to you here? Because to show you the bounding box, I would have to read the data. And then I'm back again to here, instead of using 400 megabytes of data, I use 8 gigabytes. I can do it. So that's the other point that is important here. The only object visible is the slice. See, the reader is not visible. You know that this particular icon here shows you how to turn the visibility on and off for each of your objects. So on purpose, I selected to not show it so I would not read it globally. And if I do this now, so I can select it. Well, it doesn't let me. I'll just click on it. And it did actually something funny here. Oh, yeah, no, nothing funny. There's my outline. Okay, so everything is cool. And by the way, did someone look here at my memory usage? 8 gigabytes. There. So how would you do it to avoid all this? Well, it's simple. You would just create a parallelepiped with those 8 lines, and then you'd be done. Okay? So those are all the tricks you need to think of to make an efficient use of your memory. Is this clear what is happening here? Clear to all of you? Good. So we're back here. So that update pipeline information command is exactly what takes place here. The reader says, this is the description of my data, and I pass the information along. So it's the update information pass. The reading itself does not take place. Then the slice here, for example, says, I want slice number 512. This goes up. And then finally, the execution says, the sync says, I want an image. So I trigger the execution, and the data goes down. If it's in parallel, it works the same way. And that's where we are. Now here I have to introduce a little bit more syntax through some examples. Teaching you how to use the VTK C++ library would take another 2 days of courses, maybe next year, if you're interested. But basically, how do we trigger the execution? We have an object called the VTK renderer. This is a class name. And then a renderer window. And then the command render is what triggers the execution of a pipeline. So you can set up a whole pipeline and, and then type render at the end. Oh, and by the way, I'm going to read this one more time, my little demonstration here. This optimization I have demonstrated to you here, being able to read only one slice of data, you can only do it with Python. Let me think carefully. Yes, why is that so? It's the way you build the graphical user interface through here. You say open file, and then you go to your file name, and you say OK, and here, oh, it's already done. It's because auto apply is off. So I repeat, you select your data, and then you cannot do anything else but click the apply button. And when you apply, you read the whole volume. You're stuck with it. So I read my whole volume here, and it takes a little bit of time. And then I do my slice, like not this one, but this one. And I do a 512 and 512. And there's my slice, okay? So the user interface is forcing you into reading, applying, doing a slice, applying, etc., etc. This is good for small data. But for big data, you would not want to do that. You would have to go through the Python script. All right. Now, the basic ingredients would be like this, just as a reference to sources, filters, mappers, and rendering. We would have the source of data, for example, an image data, a filter, and then the geometry, we say set input data with the object above, so we connect the source to the filter. Then we use a polydata mapper where we connect the filter to it. We use actors, mappers. Those are details about graphics. We don't need to explain all of those things. The renderer is here. And then at the very end, the render window render triggers the execution of the pipeline. By the way, in my slides, I've put a lot of material for completeness. For you, if you want to dig further at a later stage, I will take the freedom to skip some of those pages to be a little bit more faster. So let me see the time here. I forgot already what we had in our plan. Batch. Well, we're going to finish up with batch then. Not quite. I have here a wonderful demonstration that I've made up. Now, parallelism is just one way to subdivide data into multiple pieces to do visualization. There's another way called streaming. Streaming is just like YouTube or those other streaming devices. You go through some content, you read it, and then it disappears right away. But as you watch the movie in streaming mode, you have accumulated all the content in your brain, and you never had to download the whole film onto your laptop, onto your device. Well, streaming is another way for you to do large data visualization. And it will happen like this. Suppose that you have large data, and we've already discussed how when is large data dividable? Not all readers are capable of, but most of them are. If a source of data is capable of dividing data into multiple pieces, then you could very well treat the first piece, go through the pipeline, accumulate the result here, then go to the second piece, then to the third piece, etc., all of this in a loop fashion. And at the end, you have the final output, okay? So this is an example I have prepared and that you can run actually on your own laptop as well. It's called distributed image data. And in Python, I use Python 3, so I execute it like this: exec, open the file name, .read, and it basically does this. It has a source of data, a mapper, and a render. And that mapper does streaming with 4 pieces. It means that it's going to ask the source in a loop fashion for multiple pieces. This is how it will execute. If you stream the data, and this refers to the source code which I have distributed, you set the piece number and then you trigger the rendering. Or if you execute it in parallel, MPI exec, for example, on my laptop, 4 processors, the VTK Python or the PV Python will do it, and then the name of the file, and here's the output. For each of those pieces, you get the external surface here, so block 0, 1, 2, and 3. And then the final image is what ParaView gives you. It's the full volume. But here we have streamed the data. I'm going to show you this in action. And that source code, we have it, so you can exercise it as well. Distributed image test. That's what it is. So MPI exec. When you run in parallel, you always have to give full path to everything. So this is how I do things. Distributed image test. There. That's the image you see. Oh, I made a mistake, but that's perfect. That's the image you see in ParaView. If you run single processor or parallel, it doesn't matter to you, right? And I will insist again, parallelism is usually transparent to the user. If you develop a solution which works on one processor, it will work in parallel as well. In fact, this solution here works perfectly well. I have here my data set. You know, the mistake I made is that I forgot to give an option to MPI exec. So by default, it took one processor. If I now use 4, here's the answer. Well, here's one image, 2, oops, 3, and 4. Those are my 4 pieces. So this is exactly what ParaView does. If the source of data is capable of dividing its data into pieces, ParaView will do as many pipelines as there are processors with a different subpiece, and then it will combine the images together for you. So that comes for free. This is done with ICE-T, that image compositing library. Okay? We will see how you execute that example on your laptop. But basically, that's it. Here we have an algorithm called extract surface. It shows the outside boundary of a domain. Well, that is a good example for a filter which requires ghost information. Because, for example, here, you see very well that those faces here, well, this vertical face here is an internal face. It's just a byproduct of the subdivision. It should not be shown as a solid surface. So ParaView does this very well. And just when I told you that parallelism will work transparently, what number do you want? 3? Let's try with 3. Here's 1, here's 2, and here's 3. And they make exactly the full volume. This is the part over there in the back, and this part plus this part fit right here in the empty space. So basically, how does ParaView do it? ParaView looks at the global dimensions. And then it says, I have 3 processors. I have to divide that into 3. So it makes pieces which are at best exactly the same size. And sometimes, well, you cannot divide an even number by 3, so you make 6 on one side and then 7 on the other side. And that example I have made actually does exactly this. On the screen over here, it shows the global extent. So this is a grid of 31 cube. So 030, 030, 030. For each of those pipelines, they have the same global extent. And then each one uses a different set of indices. See? One of them uses 14 to 30, 9 to 30. One of them uses 0 to 16 and 9 to 30. And then the other one uses this. And by the way, look at this very carefully. Rank number 2 uses grid, a sub-extent from 14 to 30, and then another one to 0 to 16. Those 2 numbers here, 16 and 14, what does that mean? It means they overlap. That's exactly the ghost cells creation. And this is all transparent to you. Okay, ParaView does all those things to you. It's capable of estimating if the ghost cells are necessary, and if it is necessary, it computes the dimensions of each piece correctly. So there. I'll do the final, just to convince you. I'll do it with 2, and with 2 there should be no secrets. It should be exactly this, 2 halves. And again, look at my dimensions. I have 0 to 16 here and 14 to 30, which means right here on this boundary and on this boundary, I have 2 lines of cells which are ghost cells. There. All right. Now, let's go to connecting to Pitt's Dane, actually, since this is what we're here for. So there's ParaView. Has anyone ever connected to a remote server? You have, okay, so that's good. So here I have a list of servers, and basically what you're going to do is, first of all, if you start from an empty set, you're going to load a particular server description file, which I will provide to you. And then once you have it, here's Daint. Here's the interface to Daint. We need here one specific logging name for Daint. How many logging front ends are there on Daint? 6 or 7 or 5 currently? It doesn't matter. You need to pick one of them. So 101, 102, 103, 104, 105. Just pick 103, it's already there. Here you need to put your username, not my username. Your SSH command, and then the name of a remote script, which I have provided for you, which you should copy to your private home, and then you can modify it as you want. And we're going to explain what this particular shell script does. Then you select the number of nodes you want. So here, one compute node using 8 servers per node. We're going to use the norm. Here it doesn't matter. We have the choice between normal or debug queue. Here again, it doesn't matter for us because we have an allocation on the GPU partition, which has a fixed set of nodes with 64 gigabytes of memory. If you were to use the multi-core, the multi-core partition on Date, you could select standard or high memory. Here you select the version of ParaView which you need, and you should use 5.7. And here you need, as a PV server port, you need your user ID. So you SSH to Date, and you type the command ID. And that comes up with a number. It's a number that is unique to each of us, which means that the connection from your client to a computation on Date will be unique to you and will be reserved for you only. That's the purpose of it. So for the documentation, I've put my name and my ID, but you should change that. Sometimes new users forget to do that, and then I find out that I cannot connect myself, and I say, there must be a new user that has done this. Basically, that's how it works. You know what? I'm going to connect now in remote, and I'm going to show you a couple of things. I just have to get to the right place.
So can I ask a stupid question? How do you get to that configuration panel that you have?
Okay, so it's right on my slide. So I will repeat the question and.
Okay, so we'll do it later.
There. There are 2 server configuration files which you need. One of them is specific to Windows. People using Windows. There's 2 of you. 3. Oh my gosh. It's more complicated to do. It works just fine, but it's a lot more involved to do. So I'm going to first go through the explanation here for the Linux people, and then we'll go back to the Windows later on. So one of them is specific for you Windows people. One of them is for the others. This file you need to copy on your desktop. You need to edit it, change my name with your own username. Change your ID, change my ID to your own ID, and then you're done. But before we do this, actually, there's one thing I need to do. No, that's not the one. Servers. Okay. We have a special reservation on date. It's hard to say because it's in red, but it's there embedded into that shell script. So whenever I use it, I will be able to go directly get a node without waiting. Let me go back here. So this file you copy to your desktop. That file makes reference to another file name called remote connection submit pvserver.sh. This is a shell script which will generate a command, a script for Slurm. Slurm is the job allocation tool at CSCS on PID's date. So my advice is to take this file, copy it to your home, and then you can customize it again for your own purpose. Okay? In the PVSC file, there is the default ID that you need to change with your user ID from date. Here's the menu. You go to load servers, you select that PVSC file, you add it to your configuration, and then as you saw earlier when I was connecting, you get this particular menu. So here, the login name on date, your user ID. For Windows user, we use plink, so you need to have PuTTY installed. And then the rest is the same. So one number of node, 8 servers per node, the queue, etc. And then you click OK. On your console, this is the batch job that gets generated for you. So here's the example. The job name is PV server, 1 node, 8 tasks per node, 8 tasks, 20 minutes, partition is normal, constraint is GPU, and it runs the command S1 PV server, remote connection, client host is the logging name's address. The server port is 11,1100 by default, and that should not be changed because the whole purpose is to create an SSH tunnel from your laptop to the compute node. And that tunnel uses the default value 11,111. So there's a couple of sanity checks we need to do once you are connected. First one is check that you are really connected to your remote parallel server. So you go to the menu help, about, connection information, and you read that description here. Here I was connected, so it says remote connection, yes. Reverse connection, yes. It shows the Python installed on PID's date. It shows NumPy, Matplotlib, etc. And then here, it shows the OpenGL vendor NVIDIA, the driver's version, and the Tesla P100 this is the GPU we have on PIDS date. So that's the first check to do. If you are using the multi-core partition, the only difference is that here you would have OpenGL is VMware, the Ranger is an LLVM pipe, OS Mesa, and the rest is identical. So this tells you that you have a remote connection, but is your reader capable of reading data in parallel? This is how you do it. You display variable VTK process ID. So the very easiest thing to do is to create a wavelet source and to display the variable VTK process ID. So I have here a live connection. Wavelet is in the source alphabetical list over here. I go to surface mode and I show my process ID. So here, sure enough, I have 8 different colors. I have a little block of data subdivided one time in the X direction, one time in the Y direction, one time in the Z direction. And that makes the 8 pieces. Okay? So when you have that on the screen, you're guaranteed that you have a remote connection that is working properly. All right, so so that's for the remote connection for Linux and Mac users. That would be as simple as copying the PVSC file, this one, to your home, copying to your home on your laptop, then load it into the ParaView connection, copying this file over here on date to your home on date, and then you can refer to it. And then you change those lines, your default PV server port using your own ID. Load servers, and then try out the connection. For Windows users, it's a little bit more involved. And here's how we do it. We need PuTTY. We need to create an SSH key, copy that file over, copy the key over on the date side, and then load the private copy of that key into Pagent. Then we create a PuTTY session. So I call it reverse connect date. That's the best way to do it. Over here, saved session, reverse connect. Under connection proxy, you put your own username here, and then you use that particular command, which I have put here. plink your own username at ela.cscs, cscs.ch, -nc, etc. Just type this exactly as it is. This is page 44 of the notes. under remote connection, we create a reverse, well, it's called a remote tunnel. You use your own ID over here, and then you type it. You use localhost, which is 127.00.1, double dot, your user ID. You click the add button, and that creates that particular SSH port forwarding option. Save it as a session, yeah. And then the rest is the same. That file, the PVSC file, already makes reference to this reverse connect daint session. And then I will go to your own table to help you out with the details if you have issues. One thing for Windows user to be careful with, when you select the SSH command, you have the browser button here, which enables you to get to that path for the plink executable. And when you copy it, it does not add those double quotes, which I have put here. So make sure to have those double quotes around the full name. That's the only thing that's not automatic. All right. Now, I propose we take a break because they've brought up our lunch over there in the room. We have an hour of time to eat. You can, please do not bring food into the computer room, into the room here. Eat outside. When you're done, you're welcome to start right away and test your remote connection to PIDSDAINT using those instructions. And I will help you out. Okay?